Welcome everyone back to the Python workshop series, part 2 this time. We're going to be going through some of the scientific packages that come with, that we can get through Python. So I think once you've kind of got a foundation in base Python, learning how to use packages is kind of like a superpower because you're leveraging code that other people have used and thousands of people have written together, and then it's just like the code that they write is amazing and like you can kind of work within that, and it's great. So just to get started a little bit, does everyone have a Jupyter Notebook environment set up? Yes? Yeah, cool. Awesome. And in order to get the resources for this workshop, you just need to go, if you go to the Discord, in the announcements, there's a Google Drive link. If you navigate through to that, you should get to here and workshop 2. And this is the notebook we're working off today. If you just click through there. There we go. Awesome. Okay, so feel free to like follow along if you want. But yeah, everything will be on the screen as well. There's a bit of, so I guess the structure of this workshop we would have covered a bit in workshop 1. Workshop 1 we went over lots of the foundations of Python, as well as the general coding landscape, why we care about coding, stuff like that. What a Jupyter Notebook is. We'll rehash that a little bit here, even if it's just for the recording. This workshop will be going over the scientific computing packages. This workshop does assume that you're at least somewhat familiar with base Python, so just a heads up for that. If you aren't familiar with base Python, I'd recommend you watch the recording for workshop 1. And yeah. And if you can't get enough Python, bunch of resources there. There's a lot of content there if you're interested. A bit of a disclaimer. The focus of this workshop is to give you an idea of what's possible in these packages. But more importantly, it's not to give you a mastery of these packages. Mastering these packages takes quite a bit of practice. But the important thing to take away from this workshop is that in order to use these packages, they're so popular that they have a lot of really good documentation that you can just look up online. Google's your best friend in this instance. So that's the main takeaway from this workshop. It's not complete mastery, just a knowledge of where to get more knowledge. Got a table of contents. Feel free to browse through that, and that should also help direct you if you're just looking for that one thing that you heard in the workshop. Bit of vocabulary if you get confused on anything I mentioned, and cool. We'll do a bit of a recap of workshop 1, mainly just around the Jupyter environment, because that is what we'll be working in today. So in Jupyter, we have this concept of an IPython notebook. That's a file ending on .ipynb, and this, compared to a Python script, is an interactive way of coding. So you're able to intersperse code, and you're able to intersperse paragraphs, equations, and stuff like that. So in order to launch Jupyter, you can either, in workshop 0 we went through a few different ways you can work with Jupyter Notebooks, but you can either use Jupyter Lab, Jupyter Notebook. Jupyter Notebook is the program we're using today. You can also use Google Colab, which is an online environment and very easy to set up. And you can also use VS Code. So VS Code is just kind of a general development environment that you can use. And if you don't have Anaconda installed, you can just use Google Colab. And it's pretty easy to get started from your Google Drive. So just regarding your notebook, this would have been covered in workshop 1 as well, but I'll just cover it a little bit here. There's the idea of 2 different scopes. So here I'm in the command scope. So this is where you can like navigate up and down your cells by pressing up and down. And you can also press various buttons to like insert cells above. So I'm pressing A, or inserting cells below with B. You can also use Shift and up to highlight multiple cells, and double D to delete cells. So just navigating with your shortcuts, very easy way to kind of work your way around a notebook. The more you use the shortcuts, the less you have to touch the mouse. You're just flying around the keyboard, and it just makes things much faster. if you want to if you want to find some more shortcuts here, if you go to Help, Keyboard Shortcuts, they're all listed there. So we have Command Mode and Edit Mode as well. So Edit Mode is when you press Enter on a cell, and you can actually edit the lines inside. So when you're in edit mode as well, you can, a very useful thing for Python is the idea of help documentation. So if, say, I was interested in the sign function from the help module, if I just call help on sign, it actually displays documentation on how to use that function. And that's actually the same with every function, both within Python and within every package. So just calling help on that, it's a nice way to basically see what's up. And the other way of calling help is if you're inside the function itself, you can do Shift and Tab, and that brings up the exact same help documentation right there. Awesome. Cool. That's all I'll say regarding the recap of Jupyter Notebook, I guess the Jupyter environment. What I'll go through now is, I guess, the beauty of packages, right? So packages can kind of be thought of as mods for video games. I don't know if, in the sense that the bundles of code that kind of extend the base functionality, and the nice thing is with packages is they're free as well. Packages are normally oriented around solving a specific class of problem. So you might, I guess a good example is just to look at the available packages, right? So you have numpy, which is used for optimized array-based maths within Python. So working a lot with hardcore numbers and lots and lots of data points. Pandas is really good for working with tabular data. Matplotlib, Seaborn, and Altair are good for plotting. You have SciPy, which is great for scientific algorithms, so on and so forth. Beautiful soup, Selenium, docx. Docx is good for editing Word files. Manim is good for making mathematical animations. MoviePy for editing movies and videos in Python. And then Notebook is this Jupyter Notebook environment. So there's lots and lots and lots of different packages. If you actually go to the awesome Python link over here, this is actually a curated list of some really, a curated list of awesome Python frameworks, libraries, software, and resources. So there's a bunch of different categories, but you see how big this file is right here. This is all the different packages, just a curated list of really good packages within Python. So, there's probably 1,000 there. And those are just the ones that people have cared enough to put into a curated list. So the number of Python packages is really quite insane. So I guess the capabilities of Python is also quite insane. And the absolutely amazing thing about Python packages is it's not just one person writing them. With a lot of these packages are made publicly available, open source, online, mostly through GitHub. And if you just navigate to the NumPy GitHub, you can see that if we look at the number of collaborators on this project, there's over 1,000 people who have contributed in some sense to the source code of this project, whether that's fixing a typo or implementing functionality as well. So I'll just give you a bit of an example of a cool thing that's possible to do with packages. So, sorry, let me just ignore that. So a bit of an example here. Say we're interested in having a progress bar for our application. There's this great package called tqdm, which does exactly that. It gives us a progress bar. So this, on line 1 here, we have the statement, from tqdm, import tqdm. So that basically means from the tqdm package, imports the tqdm function. Now, the tqdm, I mean, the naming's a bit weird, but the name of the function is the same as the name of the module in this case. So we also import time, and then we do for I in tqdm range 100, I'm going to sleep for a 20th of a second, so I'm going to do nothing for a 20th of a second. And if I run this code, we can see that we actually get a progress bar. So you can imagine if time.sleep was some sort of intense calculation, it's really nice to have a progress bar because we can kind of see how the calculation is progressing. You can go and grab a coffee or whatever. And you can also have multiple of these progress bars after each other. So let's say I just copy and paste this a few times down here. And I can also have different descriptions here. So I can have description equals progress 1, and I can copy this down here as well and change it up a little bit. And in order to see the full settings of tqdm, I can just do Shift-Tab, and we can actually see what parameters it takes. So desc prefix for the progress bar. So that's what I fed in there. And we can see that progress 1 goes, and then shortly progress 2 will start, and then progress 3. So that's pretty neat as well. Now, I've talked a bit about packages, but there's two types of packages. There's standard packages, and then there's community packages. What I've been talking mainly is about community packages. These are packages written by the community, and many people can contribute to them. You also have standard packages, which they come with your base installation of Python. So they kind of, once you install Python, you have access to these packages. So that's stuff like the math module. Gosh, why is Unify keep asking me for the password? Anyway, so that's stuff like the math module, the OS module, stuff like that. The math module for some basic mathematical functions, OS module for interacting with the operating system. And then we also have community-made packages. Now, when we're thinking of community-made packages, these are installed by using the tool called pip. Pip is a command line tool, so we use that through the terminal. And what it does is we run pip install and then the package name. And what it does is it looks on the Python package index, PyPI, for that package, and then it installs the package from that database. Lucky for us, since we're using Anaconda, Anaconda is a version of Python that comes with a lot of the scientific packages already installed for us. So we don't even need to worry about running pip install. However, in order to get like an idea of, to see what our installed packages are, we can actually run pip list. So if I run pip list here, this will give me a list of all the Python packages within my environment. So just to expand this a little bit, we can see that we have numpy over here, and we can see we have matplotlib up here. Okay? So those are already installed. I don't need to worry about installing them. And when I'm running piplist here, piplist isn't a Python command, it is a terminal command. So here I'm just prefacing it with an exclamation point to tell Jupyter, hey, this is a terminal command. Please run it in the terminal kind of thing. So that's what the exclamation mark does at the beginning. So in order to import a package, the easiest way to do it is just import package, import the package name, and then it'll actually bring that package into your Python environment, and then you can access its functions by doing package name dot the function name. So in this case, package name dot calculate py. But I mean, you can imagine if your package name is called package name, it's not really that good, if that makes sense. It's a bit of a long package name. Having to type that out every time you're using a function, especially if you're using the package a lot, is a bit of a pain. So what we do is we can often alias a package using the as keyword. So imports package name as pn. Now, every time I type pn, it's as if I typed out package name in full, and then I can access all the functions just instead of calling package name.calculatePy, I can just do pn.calculatePy. And then, so those are two ways of importing packages. We can also actually import specific functions from a package. So we can, in this example, if I'm only interested about the calculate pi function, I can actually just say from package name import calculate pi, and I can use that function as if I wrote it myself. Within my Python code, I just use calculate pi without anything prefacing it. Cool. So that's pretty much how to import. It's pretty simple there. What we'll get into now is actually numpy. So what we'll go through is we go through numpy, and then we go through matplotlib, because numpy kind of gives us some tools that is useful for matplotlib as well. So first off, what is numpy? The best way to find out what a package is just to look up the documentation. Now, if I wanted to look up the documentation for a package, the internet. Okay, wait, give me a sec. Awesome. Okay, sorry about that. The best way to find out what a package does is to just Google numpy documentation or package name documentation. There we go. That's a documentation for numpy. And at the splash screen, a lot of them just tell you exactly what the package does. So numpy is a fundamental package for scientific computing in Python. It is a Python library that provides a multi-dimensional array object and various derived objects. So the main takeaway is that numpy provides a multi-dimensional array object. Now, you might read that and be like, what the hell does that even mean? And that's fair enough. So we'll delve into what is an array. But before we can actually do that, we need to actually delve in a little bit into what a Python list is. And also, not only what a Python list is, but what are its shortcomings. So if you've done an intro to Python unit, you'll be familiar with lists, its uses and its downfalls. The crux of the issue is that you can put anything in a list, right? So, so you can put true values, you can put strings, you can put numbers, you can put anything. And that poses two problems. Lack of element-wise operations. Now, since we can put anything into a list, we can mix and match elements in a way that element-wise operations doesn't make sense. So if you imagine we have a list of 1, 2, 3, then we might want to times that. We might want to say, oh, that represents a vector, so we want to times that by 2. So 2 times 1, 2, 3, we kind of want maybe to have 2, 4, 6 as the output. Now, the reason that that isn't the behavior of lists in Python is because we can actually put anything in that list. And if we had 2 times 1 times 1, 2, hello, suddenly timesing it by 2 doesn't make any sense, because what's 2 times hello? Like, it doesn't really make sense since we have this mix of data types here. So we can't really represent it as a vector. And in previous units, you might even have represented a matrix this way as well. In this case, I have a list of lists where each list inside has 3 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we might want to use that to represent the matrix, a 3 by 3 matrix from 1 to 9. But like, this again poses a problem of like, well, the data types, but also like the lengths of the lists. What happens if we have the second element being of length 4? That's suddenly not a matrix anymore, because matrix is like rectangular, and then you suddenly have like a piece sticking out, right? So suddenly we have some rows longer than the others, and it makes no sense for matrices to have that. So that's the first problem. There's not much restrictions on what can be put in a list. The second problem is really an issue of space. So lists are versatile and can house any data type in each of its indices. This means that each index can have differing space requirements. And since a list is a mutable type, that means we can actually change the elements in a list as we kind of work with that list. Not only is each element got different space requirements, but like suddenly element 2 can have more space requirements than it did before. So how does a list work under the hood? Let's take a look at the below example. So just ignore this here. We have my list, which is 72.1, false, and then 72. Now 72.1 is a float type. It takes up a bit more space than an integer. False is just like a switch, so that takes up very little space. And then 72 kind of in between a float and a Boolean, kind of like a medium amount of space. If we can imagine that the data in a list is stored next to each other in memory. So I'm thinking like on the actual, in the RAM of the computer, if we imagine that those items are allocated next to each other, well, we can actually quickly see that that's not going to work. So here we have list 0 next to list 1 next to list 2. As we can see, list 0 is the biggest, list 1 is the smallest. And then suddenly, if I switch out list 1 here for a bigger data type, it doesn't fit in that small slot anymore, right? So we can't really like squish it in there without having to reassign all the list values, and it's just not going to work. And I guess a little bit of example here. Here I've actually, so if we look at my list 0, that's, I need to run all this above. So I'm just going to disable these progress bars. It's going to take some time. So if we look at list 0, okay, we look at list 0, we see that 72.1, and then we can see, I guess just a bit of an exaggerated example, we can see that the first element has been switched out for the entire B-movie script, which of course is much bigger than both 72.1 and 72. So you can really put anything in a list. You can put an entire script for a movie. You can put an actual movie file itself inside a list. So how does it actually work under the hood? Lists work off the concept of memory addresses. So instead of putting the actual data itself next to each other in memory, what it does is it kind of puts an address for that piece of memory. So instead of, so if you imagine you have, so every time we call list 1, it looks for the memory ID corresponding to list 1, and then it actually goes into RAM to that corresponding ID location, and then it actually reads the data in there and passes it back to Python. And this means that we can actually, it doesn't matter, we can store our data anywhere in RAM as long as we have some free space, and then we just record the memory ID of the new location. So if we were updating list 1, we can just slot it in for this block in memory here, record that new block in, that new memory ID in the list, and then go on our merry way. But as you can imagine, if we're dealing with millions of numbers and we're updating them continually, having to look up memory addresses all the time, it's pretty inefficient. So arrays really, the benefits of arrays arrays pretty much provide solutions to both these problems. Arrays can be thought of as homogeneous, rectangular, multi-dimensional blocks of data. So homogeneous in the sense that every element in an array has the exact same data type, and because of that, has the exact same space requirements. So, and it also means that it adds an extra restriction that you can't actually slot a differing data type into an array. Like if you wanted to slot a string into an array of integers, you can't do that. So the homogeneous. Multi-dimensional, meaning that they can have more than just one dimension. So if we imagine a list is fundamentally one-dimensional. It's a sequence of elements from beginning to end. Even if we have a list of lists, it's still one-dimensional. It just has nested lists inside. An array, on the other hand, is multi-dimensional, fundamentally multi-dimensional. So you can have a one-dimensional array. You can also have an n-dimensional array, where n is whatever. So in this workshop, we'll be typically working with one-dimensional, two-dimensional arrays, so kind of like vectors and matrices, but you can have any arbitrary amount of dimensions. And rectangular in the sense that no individual row in a matrix is longer than the other rows. So it's always going to be rectangular. So the problem solved is element-wise operations. There's no differing data types. So if we do 2 times an array of integers, it's just going to do that element-wise, and that's fine, because as long as the operation, like 2 times, is applicable to the data type used to construct that array, it works. And also accessing elements, there's no longer a need for memory addresses. So when we define an array in Python, say I say x equals an array, it's pretty much me just saying to Python, hey, I need an array of 50 integers. Can you like pre-allocate that space in memory? Just like save it for me. I'm going to be using that just now. And Python's like, yeah, I'll do that. And it allocates this single block in memory, so 50 integers side by side. And now instead of having to actually get the memory address, so if I wanted the 20th element, I don't need the memory address anymore. I just kind of see, okay, how wide's each element, and then where does it start, and then I can just jump to the 20th element. So it's much faster that way. So hopefully that gives you a bit of an overview, kind of hand-wavy explanation of the benefit of arrays. But I feel like this is sufficient for our understanding of arrays, and this allows us to work with it as well. And really, the element-wise operations of arrays, super handy, and you'll actually see like the power of it through the workshop as well. So importing numpy. To import numpy, we often write import numpy as np. That's the typical way that you can import it. You can also write like import numpy as anything else, but it makes it a bit confusing if people are reading your code and you're importing it as aliases normally used for other packages, if that makes sense. But if you want to be a bit chaotic, you can do that. So normally we put our imports at the top of our Jupyter notebook, but I'll just put them all here. Import numpy as np, and I'll also import matplotlib here, just because I can, and that's going to be used later. So first off, let's create our first array and take a look at it. So here I do array equals np.array, and then inside this I put a list of lists. So the way that this is going to be interpreted is that the first list is going to be interpreted as the first row, second list is the second row. If I actually type array or print array, I can actually see that it is a two-dimensional array. It has 3 columns and 2 rows. So yeah, we've got our first array. Now, we can actually look at some useful properties of the array. We can look at its data type. So if we do array.dtype, we get its data type. It's of int 32. So that just means that, I guess the beginning bit, int just tells you it's an integer type, and then 32, the number after just says how many bytes it takes up in memory. So 8 bits in a byte. So each element there takes up 32 bytes. If we do array.shape, what that will give us is 2, 3, which indicates it's 2 rows and 3 columns. So rows, columns. If we do array.size, it'll give us the number of elements in the array, so 6 elements. And array.endim will give us a number of dimensions for that array. So it's a 2-dimensional array. So for a 2D array, the first axis, which axis 0, because in Python we count from 0. So the first axis, axis 0, corresponds to a row. And the second axis, axis 1, corresponds to a column. Okay? So kind of this is the first axis here, second axis. And the reason that I'm pointing this out here is that some operations in NumPy we want to apply along a certain axis. If you imagine we want to sum up an array, we might want to sum up the entire array, which would be taking the sum of 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, and 6. But sometimes we might want to sum along a specific axis. Like if I wanted to sum along the columns, I could get 4, 7, 9, right? So knowing kind of what an axis is and what dimension it corresponds to is good, because then you can apply it along a certain dimension. And similar to a list, we can actually slice out sections of the array. So with a list, we can use, and I know that in the previous workshop we didn't exactly get around to this, so I'm happy to go over it a bit more here. But if we have a list like so, 1, 2, 3, 4, 5, like so. If I do list colon 3, what that will do is it slices out the indices of that list from the beginning up until index 3, but not including index 3. Okay? So they'll slice out indices 0, 1, and 2. So if I actually display that, we can see that it actually sliced out indices 0, 1, and 2. There's also different ways we can slice a list. We can specify explicitly the starting point. So instead of starting from index 0, the beginning of the list, I wanted to start from index 1. So they'll just slice out the elements 2, 3. And I can also, I don't have to provide the endpoint either. Arrays work in exactly the same way, except we can actually slice along more than just one dimension. So here, what I'm doing is I'm going to slice out the entirety of axis 0, which is, so I'm going to slice out all the rows, and I'm going to only slice up to the 0th and 1st index of the columns. So it gets the first 2 columns, but still getting all the rows. And then, in contrast, the second statement here, it's taking the -1th row, which corresponds to the last row, and I'm slicing out all the columns, so I'm just going to get the last row of that matrix. I'm just going to run all above while I'm doing this. Okay. Sorry. And then, there we go. Perfect. We can also do element-wise mathematical operations with matrices. So this is what I was alluding to before. Timesing this matrix by 2 makes sense. Timesing this array by 2 makes sense. So if we just print out the array, if we do array times 2, we get element-wise times 2. We can add 2. So adding 2 to this, we don't have to add an array of all 2s. We can also just add 2, and then numpy will interpret that as, hey, they want to add 2 to every single element in the array. So you can also do that. So if we do multiply by 2, we get that. Add 2 to every element, subtract 2, divide by 2, exponentiate to the power of 2. We can, yeah, raise to the power of 2. We can do that. So yeah, element-wise operations, they work. We can also multiply whole arrays together. So we can work with whole arrays. So we can add 2 arrays together. That's the same as multiplying by 2, but we get that. We can subtract 2 arrays together, which of course just gives zeros if you use the same array. If we multiply 2 arrays together, this, I guess, is a bit different. You might expect it to, by default, do matrix multiplication, but it doesn't. It'll do element-wise multiplication. So if we multiply 2 arrays, it'll just take the first element times the first element, second element times the second element, and so on. When we're doing these sort of operations here, we need to make sure that our matrices have the same shape. Because if we're multiplying to some extent, I'll say this. Like if we add a matrix that's 2 by 3 plus a matrix that's 3 by 3, that doesn't make sense. But you can actually add arrays, like if you have a 2 by 3 matrix plus a 1 by 3 array, you can actually add those together because it'll just interpret it as, hey, they want me to add that row to every row in the array. So basically, yeah, just numpy will shout at you if the dimensions don't line up, and you'll need to finagle your way through that. And we also have matrix multiplication. So although the asterisk doesn't give us matrix multiplication, the @ symbol does. So if we use the @ symbol, that's the same as doing matrix multiplication. And then since this is a 2 by 3 array, we can't matrix multiply a 2 by 3 array with a 2 by 3 array. So if we do .t, that actually transposes the array. So I'll just show that explicitly here. If I do array.t, and if I use an uppercase T, we get the transpose. So the array matrix multiplied with the transpose of it gives us a 2 by 2 matrix on the other side. Awesome. We also have a bunch of mathematical functions that we can apply to the whole array. So there's a list of them over at that link over there, so I'll let you explore that if you're interested. When working with arrays, we want to make sure that whatever function that we're using for the whole array, it works for the whole array. So for example, if you want to use the sign function, you need to use the numpy sign function and not the sign function from the math module. Because if you use the sign function from the math module, that takes in a number, and of course we want to use a array. So just use numpy.sign instead of math.sign. So if we look here, we have np.sign, cos, tan, exponentiate, log 10, absolute, degrees, radians, and so forth. Degrees and radians convert radians to degrees and vice versa accordingly. So those are our mathematical functions. We can also write our own functions that take in arrays. We just need to make sure that as we're working with it, we're just aware that the input for that is going to be an array. So maybe we're using element-wise operations, maybe we're checking the shape, whatever. We just need to be aware of that. We can also use aggregation functions, which are very useful for summarizing data. So we can take the mean of an array, we can take the sum of an array, we can take the minimum, maximum, and standard deviation. And these functions, they actually have a bit of a shorthand to them. So instead of having to do np.min of an array, we can actually quickly just do array.min. Open close brackets, and then that's just a shorthand way of doing it. But that's only for the aggregation functions. You can't do array.sign, and that doesn't work. What's more is we can actually aggregate, and this is what I was alluding to earlier, we can aggregate along a specific axis or dimension. So if we type array.min, axis equals 0, that'll find the minimum for each column. So it'll find the minimum along each of the rows, which will correspond to the minimum for each column. So if I just run that cell there, if we print out the array, and I take the mean along the 0th axis, it'll calculate the mean of 1 and 4, which is 2.5, 2 and 5, which is 3.5, 3 and 6, which is 4.5, and it'll return that array there. And I can also just calculate the minimum for the whole array, and that's just 1. The really nice thing about these sort of functions is that once you kind of chain them together, these aggregation functions and element-wise operations, it makes doing some things like really easy. So if you imagine that we have a bunch of data that we want to standardize, calculate the z-score for, well, the way that we can do that is by subtracting the mean and dividing by the standard deviation. In order to do that, here is just a one-liner. Z equals array, take array mean, divided by the standard deviation. And that will give us the z-scores for the whole array. We can also do it, instead of doing it for the whole array, maybe we're only interested to standardize each column by the mean and standard deviation for that column. And we can do that the exact same way. We just need to specify axis equals 0. And then we can do it along the column. Axis equals 1 means that we can standardize each row. And if I actually look at Z column-wise, now it's a bit of a stretch, me, not using a keyboard for that. If we just took a peek at that, we can see that if we standardize each column, since it's just 2 rows, it'll end up being -1, 1, and so on. Cool. Okay, so that's how we kind of use mathematical and aggregation, mathematical functions and aggregation functions for arrays. We can also, there's also many different ways we can create arrays, because you can imagine if we want to create an array really quickly, at the moment we only really know how to convert lists to arrays, but we can actually create arrays straight out the gate as well. So there are many different functions that you can use. Just a bit of a note is that all of these functions you can specify the data type that you want to use. So if you want an array of floats, you can specify d-type equal float. Some of these functions will have kind of sensible defaults that they'll use. So, and sometimes they'll try and infer it from whatever you put into it. So That's just something to be aware of, but sometimes they use the default of a float64 object, which is basically just a decimal. So we have a few different functions here. We have np.zeros, ab. So ab, what we're giving there is the shape of the resulting array that we want. So we want, if we give ab, we're basically telling numpy, hey, we want a two-dimensional array with a rows and b columns. We can also do, and the fact that we say zeros is basically we want this array to have all zeros. We can do np.ones for the same effect, but with ones. We can also do np.fill, where we can actually specify the fill value. So maybe you want to fill it with -1, and you can specify the fill value that way. We can also randomly create arrays as well. So we can give it shape in there, and then it creates an array of random numbers between 0 and 1. And if we use rand n, we can normally create a normal distribution of numbers. So those are our main ways of instantiating arrays. We can also instantiate arrays without having to give the shape. So if we do zeros like, and then feed an array into it, basically what NumPy will do is it'll look at the array that we passed into it, and it'll ask two questions. What is the shape of this array, and what is the data type of this array? And then it'll create a new array with that exact same shape, with that exact same data type, but it'll fill it with zeros. So if that array had integers, it'll create an array with integers, that's the same shape. If it had float values or complex numbers, it'll create a copy of that array, pretty much, but with all zeros. We also have ones like and full like, operate the same way. I think the two most useful functions, though, for creating arrays are really arrange and linspace. So the arange function is pretty, I think the way, like, the reasoning behind that naming is it's like array range. So range is, this function is really similar to the range function in Python. So what it does is, given a start, stop, and a step, it creates an array of evenly spaced values that go up from start to stop, excluding the stop point, and it goes up by increments of step. The difference between this and our normal range function is that range only works with integers. So range, we have to give it an integer start, stop, and step. This works with decimals as well. And obviously, of course, arange, it will actually return an array where the range function will return a range object, which is to be used internally by Python. And then, so that's our first useful function. The second one is linspace. And linspace kind of flips the problem on its head. Because in order to, say we wanted an array with like 100 data points distributed from 0 to 10, like evenly distributed. What we could do is we can actually determine the step from like that parameter, like those requirements, and then use np.arange, or we can use np.linspace. So linspace, we basically say, we give it a start point, we give it a stop point, and then we give the number of points that we want within that. And the an important distinction here is by default, it'll actually include the endpoint. So say we wanted 101 numbers between 0 and 10, then it will evenly distribute that, but it'll actually include both endpoints. But if you don't want that to be the case, you can say endpoint equals false. So here are just a few examples. I think the ones like an array, those are pretty intuitive. So if we look at array is an array of zeros, so a 4x4 array, and then a full like is the same shape. But if we look at linspace down here, what we're looking at here is we're looking at an array from 0 to 100, and we have 15 data points in there. So if I look at x, we can see that we have 15. If I just do x.shape, we have 15 data points, and we can see that the start is at 0, the stop is at 100. Awesome. So from what we've covered so far, we can quickly create arrays of any shape and apply any formula that we want to them. So I guess let's compare that a little bit to what we would do if we were just working in base Python. So in this instance here, I'm creating 40 numbers from 0 to 10, and then I am calculating sine of x to the power of 2 plus 2. So this is my x array here, and then this is after I apply that function to every single element within that array. And now if we try to do the exact same thing in base Python, we have to use lists. So we kind of need to import math, then we need to create our start, stop, and our n values. We need to determine our step size, and then we need to kind of iterate through and kind of add start plus I times step and append that to X list. And then, so we need to use that to construct the X list, and then we need to construct the Y list from the X list as well. We get the exact same result, but of course, this is just 2 lines, where this is however many I've got there. Cool. So hopefully that kind of provides a bit of insight. The really useful thing with this as well is that basically what we have here is a bunch of different points. So of the function sine of x squared plus 2. Now if you imagine we wanted to plot this, if we plotted a scatter plot of this point, it'll kind of scatter the points on the plot and would kind of roughly see the shape of sine x squared plus 2, but in the domain of 0 to 10. Okay, let's go quickly through masking. So at the moment we know how to create arrays, we know how to apply mathematical functions to them, we know how to aggregate them, but sometimes we're actually interested in more than just doing those functions. Sometimes we actually want to kind of reach into the array and change the values based on the array's internal state. So maybe if the array's values were below 0, we wanted to actually bring those up to 0. So if they're below 0, we want to actually reset all those values to 0 and then leave the ones above 0 unchanged. Now we could use a for loop. We could actually iterate through the array, you know, kind of what you could do is you could like, you could use a for loop to iterate through the rows and the columns, and you can change them one by one, but there's a much easier way to do it, and that's through masking. So from what we've covered so far, we know how to index an array. So we can index an array using numbers, but we can also index an array using what we call a mask, which is an array of the same shape, but instead of numbers in it, you have true and false values. So I'll show that here, where if we have an array, which is the numbers from 0 to 10, but 4 points, so it'll just end up being 0, 2.5, 5, and 7.5. And I have a corresponding mask of true, false, which is also an array. So here I first print out the array, I then look at the mask. I can do array and index along that mask, and I can set those values to -999. So if I do that, everywhere where the mask is true, it'll replace those values for -999. So if I look at the resulting array, we can see since the 0th index is true, it'll replace that for -999. First index is false, so it leaves that unchanged. Second index, is true, so that gets replaced. Third index is false, so that is left unchanged. And this works for any array shape, as long as what mask we're giving to it is like the exact shape that it needs to be. And what really makes this powerful is that there's multiple ways we can generate masks. We can generate it explicitly like this, like what I've done here, just specifying np.array and then the booleans. But a much easier way is to use a logical operator. So just like our addition and subtraction and stuff, that works element-wise, so do logical operators. So if I look at array and I say array greater than 0, it looks at every single element in that array and asks the question if it's greater than 0. And if it is, it puts it returns a new array with the corresponding values in those slots. So if we look here, we print out array, we have a negative number, positive, negative, positive, and if I ask the question if it's greater than 0, the first one is false, second one is true, third false, fourth true. Okay? So that's a quick way that we can construct these masks. So you can ask if it's greater than 0, less than 0. You can ask if it's even, whatever you want really, as long as it's just element-wise. Cool. So if you now just ignore everything below here from line 10 onwards, let's focus on the top here. So let's use masking to create the function f of x equals the maximum of sine x and 0. Now, this notation is a bit weird. Basically what I'm saying is, think of the sine x function, and everything that's below 0, we're actually going to cut that out and set it to 0 instead. So if you imagine n equals 100, this just specifies the resolution of our array, basically how many points do we have in this array. And we generate the linspace from 0 to 10 with 100 data points. And I take sine of x and assign that into f of x. If I ask the question, where is f of x less than 0, it gives me an array of booleans and stores that in for mask. And then what I can do is I can do f underscore x mask and set everywhere where it's less than 0 to 0 and kind of flatten that out. Now, it's a bit difficult to actually visualize that, just like if we looked at the bare arrays. But what we can do, and this is what we'll cover in the second part of the workshop, is we can actually plot it out. So if I look along the blue curve, so if these are our x values along the x-axis and our f of x along the y-axis, we can see the original sine curve follows a sine curve, and we can see that the function that we just created, it zeroes out the regions where it's below the x-axis. Does that make sense? Cool. Awesome. So that's a really nice way that we can use masks. And of course, like a bit conceptually, it's like, oh, how do we even do that? But once you kind of think of things in terms of masks, answering a question like that becomes pretty easy. And then this power gets even extended because there's different ways that we can combine masks. Because sometimes we're not only interested in whether a value is less than 0, we might also be interested if it's greater than 0 and less than 2, so maybe within a range. So the way that we can combine masks is by using the NP logical AND functions. So if we do NP logical AND pass it a series of Boolean arrays, so a series of masks, it'll basically return an array of Booleans, which is true if all the Booleans in the input arrays are true. So in the context of array 1, 2, and 3, the very first cell, that will only be true if all the very first cells and all the corresponding arrays are true as well. And then these also need to be of compatible shape. We can also do logical OR, which pretty much the same thing with OR, and we can also do logical NOT, right? Now, you can imagine if you're working a lot with masks, having to type logical OR, logical NOT, logical AND. Having to do that a lot of times is a bit of a pain. There's a really nice shorthand, which is just array 1 ampersand array 2, and that's equivalent to just doing np.logical AND array 1 and array 2. So you can just slap the ampersand and you get that. You can also use a vertical bar for OR, and you can use the little tilde there, which is underneath your escape key, in order to do logical NOT on an array. And you can imagine that this actually becomes really useful because say our question wasn't when it's less than 0, but when it's greater than or equal to 0, if we just put a logical NOT in front of here, it flips out the question on its head. So everything above 0 gets flattened and everything below 0 remains the same. So that's just one keystroke and it changes the entire behavior of our function of our block of code up there. Awesome. So that's how we can do logical operators, and then we also have We can also aggregate along this. I don't know if aggregate's the right word, but we can also look at an array and ask the question, are any of these values true? In which, if we do np.anyArray, it'll actually just return true or false. So it doesn't return an array, it just returns true or false. And we can do the same thing with np.all. So just a quick example here, where we just ignore all this code down here. We'll just focus on the top bit. So we assign g of x to be np sin of x, and we construct a mask that is only true if it's above 0 and it's below 0.5, right? And then, so we have an array of values that is true only for that region. By negating it, we have an array of values that is only true for the outside regions. So for the outside regions, which is what I'm doing by negating the mask, I'm looking at the outside regions and I'm saying, okay, we're actually going to assign those to 0.25. So everything outside this band of 0 and 0.5 gets assigned to 0.25. If we look at the plot for this, we have our orange plot, which we looked at before. It creates this green plot. So it kind of starts off along the curve. As soon as it gets to 0.5, it snaps down, rides along 0.25, and then as soon as it dips below 0.5 again, it goes back up and follows the curve. And then as soon as it deviates below 0, it snaps to 0.25, and so on and so forth. Now, I guess the important thing to realize here is the resolution. What happens, we can see that along this plot, arrays, they're not continuous. They're discrete values, the set amount of values there. And we can actually see the data points here plotted along the curve. So every data point corresponds to a new element in that array. And it's at a set x interval. So every, however many, whatever the step size is, there's 100 points along here. What happens if I change the resolution to 4? Suddenly our plot becomes very ugly because it's not a sine curve anymore. Because we've only got 4 points, it's difficult to resolve a sine curve with only 4 points. If I bump this up to 20, it still looks a bit janky, but I mean, it's kind of a sine curve there. If I bump this up to, say, 10,000 or like 100,000, hey, that was still pretty quick. I mean, you can imagine 100,000 data points. It just covers the whole thing. And yeah, so I mean, like some calculations, you're like, oh, that might take a while, but sometimes Python surprises you and it doesn't take a while at all. Awesome. And then, of course, we can do the same thing here. All I've done here is actually I've hidden the markers, but so it just displays the line, but it's still discrete behind the scenes. Okay, a bit of advice when using, there's more NumPy topics that you can talk about. You can talk about concatenating arrays. So maybe you have an array and you want to slap some extra columns or rows onto it. You can do that. So you can think of concatenating arrays, pre-allocating arrays and slotting numbers into them. So it's not that huge of a topic that. It's basically like you can pre-allocate an array. So that like do numpy.0 as this. And then you can use a for loop and indexing to actually like put numbers into that array, like one at a time. And sometimes that's really useful if you're doing certain calculations that are like difficult to do within NumPy itself. And you can also reshape arrays into different dimensions. So say you have a really long array that is like, and you can actually reshape that into a data cube, but we won't cover that here. And you can also do the opposite, where you actually flatten out an array into a single line. Cool. A bit of advice when using NumPy. When using NumPy, it's important to try to avoid using for loops where you can. You can pretty much do anything using for loops and using the logic that Python gives, but a lot of the time it's easier to do it in NumPy. We'll look at a little example there. But so yeah. Implementing a solution in NumPy is often much easier to write than implementing it from scratch. So sometimes you can write a solution in 10 lines that would normally take you like 100 lines to do by scratch. So I just recommend you look for a way to do it in NumPy first. And the second reason for working in NumPy as much as you can is a bit sometimes it's a bit difficult to see. If your code isn't demanding at all, you won't even see the difference. But if your code is very demanding, you'll actually see speed improvements by working directly in NumPy. And that's because NumPy under the hood is actually written in C, which isn't Python. Python's a bit of a slow programming language, but NumPy is actually, since it's written, its base functionality is written in C, it's actually much faster. So you interacting with NumPy, you're basically giving it the instructions, and it does all the hardcore processing in C. So kind of maintaining within that, keeping your code working in C as much as possible means that your simulations run faster. And yeah, so NumPy actually takes advantage of vectorized operations. So yeah, much faster. Cool. And yeah, the more you know about NumPy, the easier it will be for you to use it to its full capacity. Make sure you read the documentation, read the doc strings as well. And if you don't know what the best way of going about doing something is, Google's a good bet as well. Just Google it. Often someone has answered a similar question to yours, and you can kind of use their answer to help as well. And it's not really just to kind of get out doing it. Often you can actually like create a solution, but just your solution might not actually leverage NumPy to its full capacity, if that makes sense. So looking online, you're like, oh, I didn't know about that function. Then you can actually implement it that way. Cool. Here I'm just going to do a bit of an example here. So I'm interested in whether this array, 1, 2, 3, 4, 5, is monotonically increasing. So basically, is every element of it bigger than the last? And I could, of course, use a for loop to solve this problem. I can also just do it directly through NumPy. So np.diff x. So if I just run this array quickly, if I look at this, np.diff gives me the difference between each element in this array. So you can see that it's of shape, it's 5 long. Me doing np.diff makes it 4 long, so it calculates the difference between each element. And what I'm doing here is I am saying, is that difference bigger than 0? All those differences are bigger than 0. And then by me putting a .all at the end of there, this here returns an array, and then this here returns a Boolean after that array is created. So I just print that out. The array is monotonically increasing is true. And of course, if I change this to like a -4 over here, I end up with a -6 there, which of course would turn that to false. Awesome. Cool. So hopefully that gives people a bit of a foundation of NumPy. Let's go on to matplotlib. I know that, yeah, I guess we'll get some practice in of NumPy and matplotlib. I think if we're able to get to the end of matplotlib as well, it kind of allows us to practice in both at the same time, and then you can actually see what you're manipulating as well, because that's the important thing with what we're doing up here. That's why I was kind of bringing matplotlib into the fold there. Okay, matplotlib. What is matplotlib? Just like we were doing with NumPy, let's actually look at the matplotlib documentation. So what is matplotlib? Matplotlib is a comprehensive library for creating static, animated, and interactive visualizations in Python. Matplotlib makes easy things easy and hard things easy. Oh, wait, never mind. It makes hard things possible. So yeah, I think matplotlib is one of those things that's like, if you really want to do very like nitty-gritty visualizations, like you want to control every single thing, you can do that in matplotlib. It just requires a bit more work, but all the things that we'll be doing are relatively easy anyway, I guess, in the grand scheme of things. Cool. So in order to import matplotlib, we need to import the matplotlib.pyplot submodule. So pyplot is basically a submodule of matplotlib, and this is the main interface in which we interact with matplotlib. So if we run from matplotlib import pyplot as plt, the way that we read this is, yeah, from matplotlib import the pyplot submodule, and we're going to call it plt. Of course, I ran that at the top of the script, at the top of the Jupyter notebook, so I don't need to run it again. But if you're importing it for the first time, you can do it there. Cool. Now, the way that matplotlib works is it works off the idea of a hierarchy of objects, right? So if we imagine we have a huge canvas in matplotlib, that canvas can be composed of multiple plots. So we can have maybe a grid of 5 by 5, and each of those slots, we have maybe a line graph there, scatter plot, pie chart, and many different plots on each of those within that figure. So in matplotlib, we have the figure, which corresponds to the whole canvas, and then we have the axes. So the figure contains one or many axes objects, and then the axes object are individual plots. Now, the axes object, the reason I'm calling it that is because it is called the axes object, and it's composed of many axis objects. So the axis is the individual y and x axes objects there. It can get a bit confusing, but that's a vocabulary that they've used for these. I guess it would make more sense if they call those plots, but oh well. So, and I guess when we're thinking of object-oriented, the main thing here is that I guess when we use the object-oriented API, and API, when I say API is just a way of interacting with matplotlib. So the object-oriented API, basically by defining this figure and axis objects, and if we assign those into variables, then we can do ax.plot, and it'll plot on that axis, on that axis object. And we can do fig.change figure size, and that we can actually change the size of our canvas. So it's just a nice way of targeting individual elements of the matplot of individual objects within the hierarchy and changing them as we want to. This hierarchy actually extends further down, so you can even decompose things into lines and stuff like that. But for a lot of the stuff that we're going to do, we don't even need to do that, and we can just work directly with the figure and axes objects. Awesome. Hopefully that kind of makes sense. So how do we create a figure and axis object? We can use the plt.subplots function. So this is the function that you use that will generate your figure and axis objects. And if we pull up the documentation for this function, let's actually just pull up the matplotlib documentation here. We can see that it creates a figure and a set of subplots. We feed it in some parameters. Now these parameters are actually optional, so we don't need to put them in. And the way that you can tell that they're optional is because when it says the parameter equals a number or equals something, it's indicating that it has a default value. So you don't actually need to feed it any parameters, and what it returns is figure and x, which is either an axis or an array of axes. Now, the subplots function, we could either, by default, it'll give back a figure with one axis object in it. But if, say, we wanted a grid of axis objects, we can say we want 4 rows and 2 columns, and it'll give back an array that's 4 by 2, and that array is full of axis objects, if that makes sense. So using numpy, our newfound superpower, we can actually pull out those axis objects individually and plot against them. And we can also use the multi-dimensional indexing to kind of index along certain columns and rows. Awesome. So let's just look at a quick example here. I have a cool plot here, and I'm just generating some data there, which just doing using numpy. I'm doing fig, ax equals plt.subplots. So plt.subplots returns a tuple of fig, ax, and I'm unpacking that into the fig and ax variables there. So that's what the notation there means. And then what I'm doing is I'm doing ax.plot x, y. So if we look at the plots documentation here, this plots y versus x as lines or markers. And it has documentation there. Then what I'm doing here is I'm setting the x label, I'm setting the y label, I'm setting the title, a cool plot, setting the x limit, setting the y limit, and then I'm showing the plot. There we go. We've got a nice plot. All this stuff here is just, I guess, stuff you can also look up on the matplotlib documentation website. So it'll tell you all the different things you can set on an axis. And you can also come back to here for future reference as well. So, and the best part about the object-oriented API is that it makes it really easy to work with multiple plots. So here, instead of fig, ax, I use fig, axs, which indicates multiple axes objects. Now, that's not proper English, but if we put an E in the middle here, it becomes a bit ambiguous whether we're talking about one axis objects or multiple axis objects. Anyway, so we just leave the E out. So if we run this, now we have x, y1 and y2, so we have x squared and x cubed. And then along the the leftmost plot, which is axis index 0, I'm going to plot x, y1 with the label y equals x squared. What I've got here is actually LaTeX, so we can have LaTeX in our plot names and our labels, and I'll format it correctly. And then here, instead of doing what we did up here with set x label, set y label, set title, we can actually do that all at once using .set. X label is this, y label is this, title, xlim, ylim. So just a nice, easy way of doing things. And then since we passed here a label in for our curve, we can do axs0.legend, and what that'll do is it'll give us a little legend here indicating what the curve is. And this is really nice. You can imagine we can actually plot multiple curves on the same plot, and we can give them different labels, and it'll give us a nice legend there. We can do the same thing on the second plot. So on the second plot, we're going to plot y2, which is y equals x cubed. And we're also going to activate the legend on the right-hand plot, but we're not going to set any of the labels because this is a bit of a construed example, but yeah. So here we don't have x, y, or the title up there. If we do fig.titleLayout, what that'll do is it'll just space everything out nicely, because if we actually disable this, we can see that the tick mark there is starting to overlap with the left-hand side. So by doing title layout, that's basically telling matplotlib, hey, I'm leaving the adjusting up to you. Cool. So that's pretty much the foundations of how to use matplotlib. The main thing with matplotlib is there's so much you can do that it becomes a thing of like, I mean, how much did we cover in a workshop, right? I don't want to be listing, oh, this is how you change the color to green, because that's a bit, it's not a good way to learn. The best way to learn, actually, of matplotlib is to look at the tutorials, yes, but also the examples. And this examples list is humongous. There's so many different examples here of all the different things you can do. And the best way to learn is actually just to look at, say, okay, I'm interested in lines, bars, and markers. Ooh, I want to do a grouped bar chart. Let's look at that. Oh, this is the code for everything. Let me copy this code. Let me paste it in a cell here. Let me run it. Oh, that's what it generates. Okay, let me kind of reverse engineer this because I want something similar to this, but I want to kind of like tweak it, right? So then you can kind of go in, you can kind of look at what each line does, and you're like, okay, that is how, you know, and you can kind of like freestyle on it, and if you break something, you can just Control Z back to a working state. So that's the best way to learn, really. But yeah. We'll just, so that's what we'll do at the end of the workshop. But for the time being, we've got a tiny bit more that I want to mention regarding matplotlib. And that's the thing is, matplotlib actually has two APIs. And I'll just briefly touch on this because if you look at resources online, you might see one API and not the other. So it's a bit of a story of two APIs. So what we've gone through is the object-oriented API. There's also the pyplot API. Now, what the pyplot API is its sole purpose pretty much is that it just exists for MATLAB users who are trying to migrate over from MATLAB into Python. So if you're very familiar with MATLAB, the pyplot API will be very familiar to you. And you can, if you use that, it's like the code is pretty much exactly the same. So if you're coming from MATLAB, definitely check out the pyplot API. Will definitely be easier. But the main difference here is with the object-oriented API, we deal directly with the object hierarchy. Whereas with the pyplot API, it's more state-based. So when I say state-based, with the object-oriented API, we're looking at an axis object, and we're plotting directly on that. In the pyplot API, when we plot, it'll kind of plot on an axis object, but if we want to change to another one, we have to like kind of flip a switch by like actively changing that axis object and then plot directly on that. So sometimes it's less clear where you're actually plotting unless you read the whole code, whereas with the object-oriented API, you can kind of see exactly where you're plotting. Because if I look here, I can see, oh, I have two axes objects, and I look here, oh, I'm plotting on the second one, right? So, and all the examples in the example section here, these are all done with the object-oriented API, and matplotlib recommends that you work with the object-oriented API. Just a bit of a note, some resources, especially this YouTube series I found, focus mainly on the matplotlib API, no, sorry, the MATLAB API. So just be aware that like if you see lots of calls to plt dot and they don't deal directly with the figure and axis, they're probably using the pyplot API. Let's just look at a bit of example. So we've already seen the example of this cool plot. If we want, we can do the exact same example using the pyplot API, and you can see instead of defining fig comma x equals plt.subplots, I'm just doing plt.plot xy, plt.xlabel, and so on and so forth. But it's a bit, there's no like set variable here, and it's a bit confusing which axis we're actually plotting on, especially when we have multiple axes in the plot. Anyway, I just recommend the object-oriented API. We can do something a bit more complex over here. So instead of just having one curve, we can have two curves. So here we're plotting two curves, giving them the label f of x and g of x. So I'm plotting sine and cos of x, and I can actually fill between these different curves, and I can say I want to, so if we actually look here, the beauty of Jupyter, we can actually see the documentation live. So x gives the x coordinates for the nodes between the curves, defining the curves. Y1 is the coordinates of the nodes to find the first curve, y2 the second curve, where we can basically give it a array of booleans in which it's going to fill between, and then we can give it a color as well and an alpha value. So alpha just changing its transparency. Awesome. And there's also a variety of styles in matplotlib. So you might see a lot of the sort of default style, but we can actually change it. So if you're used to using R, you can change the style to ggplot. And then, especially if your supervisor say they only like people using an R, you can kind of like trick them into thinking that you use R. So here I'm just generating a bunch of random numbers and scattering them across the plot, but this is just to show that this is the ggplot style. And we also have just for a bit of a Easter egg, we also have the XKCD theme. So if you're familiar with the comics, you can create plots like that. So here is finding a pebble, odds on living past 50 and years after finding, and the love for my uranium pebble from 0 to 10. So yeah, odds of surviving exponentially decreasing there. And then we can, of course, disable that as well. Awesome. So now we're familiar with the general structure of matplotlib, the two different APIs. We're also familiar with numpy, how to generate arrays and how to use them and plot them as well. Rather than going over bucket loads of a syntax, like, oh, how do you do a dotted line? What about a dashed line? The best way to learn is just by looking at those existing plots. So to get some practice in, let's do the following. think of a plot that you'd like to make, literally any plot that you can imagine, even if you have no idea how to code it up. Then look through the many matplotlib examples for something kind of similar to what you want to do. You can even change your mind here, say, actually, that plot's kind of cool, I want to check that out. And copy and paste the example code into your Jupyter environment and run it, just to make sure it works. And then look at the example and try to understand what each line is doing. Feel free to experiment, and then adapt and run the example until you get to the original plot that you envisioned. And this sort of iterating is really good to learn because it's easier than kind of starting from a blank canvas and then creating something working first try, if that makes sense. And alternatively, if you have maybe you're working on a Math 302.4 project or something and you have work to do for that and you want to plot, feel free to work on that, and we're happy to come around and help with that as well. So yeah, let's do that. Awesome. That's the end of the workshop. There's a bit of a 2-minute survey there if you want to fill that out, help us out for when we next run the workshop, but that's pretty much it. Let's get some practice in.